All right, welcome to lecture. We'll get started here in just a sec. And we're starting on the very last chapter. That's always a good thing. And again, these notes should be up there if you need them. And again, we'll get started here. Just give everybody a chance to get in. Okay, so like I said, we are starting with kinetics here. Okay, so like I said, this is the last chapter, so we're down to 2 weeks. So we got 8 days, they say, so that's good. So the last chapter we got is kinetics here, and so we're going to finish up talking about sort of the rate of reactions. So how fast, how slow. We'll also talk a little bit about catalysts, temperature, and the effect on rate. And towards the end of the chapter, we'll talk about mechanisms and sort of what's involved in that, how maybe reactions proceed in a stepwise fashion. So let us get into here. All right, so a lot of what we talked about sort of in some earlier chapters dealt with the idea of thermodynamics. And if you remember when we talked sort of about thermodynamics, really what we were focusing in on in those type of problems or in that chapter was really the idea of whether or not a reaction would take place. So a lot of what we talked about was whether or not the reaction was going to be sort of spontaneous or non-spontaneous, or we would expect the reaction to proceed, from reactants to products, or products to reactants, depending on which way it is. So that's really what thermodynamics sort of deals with. And as we talked about when we were talking about it, that it doesn't necessarily mean, for example, if a reaction is spontaneous, it will occur like super fast. It just, again, means that under those conditions, if that reaction is spontaneous, it should occur. It may occur really fast. It may occur kind of slow. But, under those conditions, it should sort of occur. And again, that's really what thermodynamics is. Thermodynamics focuses in on when we talk about sort of entropy, Gibbs free energy, all that kind of stuff. With kinetics, what we're really looking at, though, is really that idea of how fast, or I guess how slow a reaction may take place. And that's really sort of the area of study that is sort of kinetics. And one way that we look at sort of how fast or slow a reaction is taking place, we oftentimes will look at sort of what is referred to as the reaction rate. And the reaction rate is really the change in the concentration over a period of time. So most common unit of concentration, as we're familiar with, is molarity, right, which is our moles per liter. And so a lot of times when we talk about reaction rates, we oftentimes will have units of molarity over seconds, for example. So, when we do experiments, for example, in the laboratory or something like that, obviously we don't usually let it run for, days or hours or stuff like that. So usually units of time, there's a lot of times seconds, sometimes minutes, occasionally can be other things like hours, days, or whatever it may be. But in sort of the practical application of reaction rates, usually you don't sit there and for days run a reaction and stuff like that. So a lot of times when we deal with the sort of time aspect of it, seconds is a very common unit. Again, doesn't necessarily have to be always seconds, but that's sort of the idea behind that. So if we sort of look at a particular reaction here, and again, in these reactions, slightly different than a lot of the reactions that we've been sort of talking about in this chapter. Here, usually we're going to be focusing on sort of like one-way streets. So one-way reactions where we have our reactants going to our products and sort of a one direction sort of way. So when we look at a reaction such as A going to B, we can basically make some pretty safe assumptions in this case. We should expect that as this reaction begins, the amount of A should start to decrease, right? In order to make our product, we pretty much have to use up our reactants here. And in this case, A is the only reactant. So the amount of A should sort of be decreasing with time. While on the other hand, we should start to see a increase with B over time as we start to make our products. So we can represent this with these sort of little characteristics here. And these are what are sometimes referred to as, some people refer to this as the rate expression. It's kind of like calculus, right? So we have basically the change in the concentration of A. And a reminder that when you do see those brackets, that means concentration, right? And a reminder again that the concentration is typically molarity. It doesn't have to always be, but again, since it is sort of the most universal sort of unit of concentration, is often the ones we deal with. So we have the change in concentration of A over the change in T, which is time. And because this is the reactants and we do expect it to kind of decrease with time, we do put this negative here to show that the concentration is changing sort of in the downward fashion over a period of time. And we could write a rate expression here for B, very similar. We'll have the change in the concentration of B over the change in time. B being a product, we would expect again this concentration to increase with time, which means we don't have a negative here, it's positive. And again, it's a change in the concentration of B. And in this case, that essentially means that you take, final minus initial concentrations, right? Is how you would find the change in the concentration, just like you would do, obviously, final minus initial time, right, to do the change in time over that. So typically when we look at each of the sort of components of a reaction, the reactants and the products, when we're talking about either a reactant and how it's changing with time, typically that should be a negative sort of number in terms of molarity per second. When we're talking about a product, it should be a positive number per second of time. Now, when we talk about this guy, which we'll see here in just a second as well, the rate, that is typically a positive number. So the actual rate of the reaction, the average rate of the reaction is typically a positive number when we see it in a sort of problem or use it in a problem. We'll talk why that is or how that gets to positive for our reactants in just a second. So in general, a lot of times we can visually sort of look at a reaction here. So for example, if our A going to be the A are the sort of black circles there, the B is the red circles, and you can see at time 0 in this graph, we have pretty much all of A present, which is what we would expect to happen, right? Again, since this is a one-way street and the reaction is heading in this direction, we should see, as we do here in this graph, a decrease in the amount of A. While we are also seeing in terms of B, we're starting with nothing, but we are getting this nice increase that's basically happening. So the forward reaction obviously is happening since that's the only reaction that's happening. And we could gradually see a lot of these sort of black circles get replaced with the red circles. until, you know, we pretty much have maxed out our product formation on their side. And again, in kinetics, in this chapter, much like in a lot of the other chapters where we use ice tables and stuff like that, but in this particular chapter, they like to use a lot of graphs, a lot of tables and stuff like that. So not so many ice tables or anything in here in this chapter, but a lot of graphs that you will see, and a lot of table information will be given to you in these problems. Here's another way that we can sort of visually follow what is happening in terms of the concentration in a reaction. And we could do a very simple sort of experiment, very similar to ones that you've seen videos of this semester, and probably ones that you maybe have done before. Again, the use of some type of spectrophotometry, some type of absorbance readings allows us to follow what's happening in a particular reaction. So for example, here, if we have this reaction that's up on top, pretty much this guy is causing this color here. And as this reaction proceeds to the right-hand side, pretty much everybody over here is sort of colorless. So we can see just visually here in the beaker, the reaction is proceeding to the right and the products, and we can visually see it as the color is changing, right? And as the color starts to change here, that means we have less Br2 in this case, and we know we have more of our products that have been formed. And one way we could do that is, much like we've done many times here in some of those labs, we could get the maximum absorbance, right? So whenever we do any type of absorbance, we do always want to sort of figure out the maximum absorbance, right? Or the maximum wavelength for absorbance. And again, just as we talked about a number of times, that allows us to make sure that when we do run our samples, all of our samples will essentially be on the scale, right? So that's where it maximally absorbs. So any sample that we run, the absorbance value should fall within that range and be able to be read. As we know, absorbance basically means the amount of light that goes into the sample and gets absorbed by the sample, doesn't make it to the detector. And that obviously is related to color. So in terms of those 4 beakers there, we would expect probably the guy on the left there to probably have the highest absorbance, and the absorbance values should start to decrease as we move to the right there. And that falls in line with our products being made as we go to the right. And one thing that we can know using something like Beer's law is we could use something like Beer's law to relate, right, absorbance to concentration. And a reminder, Beer's law is A is equal to, I apologize, I don't remember what, I'll go with these. I think that's what they use that's a school. Some schools use different symbols, but the absorbance equals the molar adsorptivity, the path length times concentration. Again, some places just combo those as Beer's constant. But basically, we could figure out the absorbance value, the concentration value, by taking really concentration equals the absorbance divided by Beer's constant. And one thing that we know is, as we just talked about, that the absorbance value is obviously related to concentration. So the darker the color, the higher the concentration. So we could use something like absorbance values to say that the change in the concentration of something like Br2 is proportional, that's what the little symbol means there, to the change in the absorbance values that we see. So this is a very simple sort of experiment that you could run to really figure out sort of kinetics-wise what is happening here. Now, there's problems sometimes when people do these type of experiments, because some experiments, because they change in seconds, happens super fast. At one school I teach at, they do a kinetics experiment where literally if they mix the stuff together and they take like just a little too long to pour it from the beaker into the little cuvette to put it into the spectrophotometer, if they take too long to do that, the reaction's over by the time they actually get it in there within, like 15 seconds, 20 seconds. So sometimes reactions can be really fast, and sometimes this can be a relatively difficult process, especially if you are a little slow kind of moving everything in there. But if you're really sort of fast and sort of efficient, you could really get some good information, but it does depend on the reaction as to how fast or slow it does take place. So if we look at sort of information, say, which is typical information that we would get from, say, an experiment such as this one here, typically this is sort of the information that we would sort of graph or sort of get. And we have time versus the concentration of Br2. And as we can see here, since Br2 is a reactant, we see that over time it is starting to decrease, right? So the amount of Br2 concentration is decreasing over time, which is what we would expect. And there's sort of two rates that we sometimes talk about. For example, a lot of times we talk about the average rate, which is sort of the rate for the entire reaction as a whole. And that, again, in this case for Br2 would be minus, because it is a reactant, and it would be minus Br2, change in Br2 over the change in time. And again, that would be the final concentration of Br2 minus the initial concentration divided by the final time minus the initial time. Now, there's also that instantaneous rate, which is the rate for a specific sort of period of time. So you could sort of think about it like when you drive, right? So say the speed limit is, 65-ish, I suppose, depending on where you're driving. So at some point along your trip there, perhaps, you're at 65, perhaps you're at 70, 75, hopefully not more than that, 80. Maybe on your way to Arizona, it's like 75 out that way. So, you're 75, 80 at some point. Hopefully you're not instantaneously at 80 when the cop is behind you, right? But, if you averaged out your whole entire trip, for example, from beginning to end in terms of how fast you were driving, maybe you were averaging about 65 miles per hour. But, at any given point in time, if you just kind of take a window of time within your trip, you may have been traveling at a much faster rate or maybe even a slower rate than on average, it will average out to wherever it's at. So that's sort of the idea there behind average rates and sort of instantaneous rates. Usually average rates, again, is in terms of experiments, usually over kind of the whole period of time for the experiment. Instantaneous rate is sort of a window of time in that experiment. And that's, for example, here, you could take like the slope of the tangent, which sounds very calculus-like there, where you can figure out basically the rate, again, for just sort of that window of time that's occurring. Now, if we take some more information from a reaction such as what we got going on there, we do see a couple of relationships in terms of kinetics that's sort of important. And if we look at our time and our concentration of Br2, for example, and we look at just sort of the rate here, we do see some variation in the rate that's occurring over sort of a specific period of time. So for example, 50 seconds, 100 seconds, and so forth. But there is sort of a relationship that basically is constant. And that's what this last column here, and that's what the little k is. So the little k is what is known as the rate constant. And for example here, this is an example of a rate law, k times Br2. So this right here is what is known as a rate law, and we'll talk more about that a little bit later on. But the little k here, if we just rearrange and solve for it, is equal to the rate divided by the concentration of Br2. This little k is, again, what is known as the rate constant, and is not to be confused with, obviously, the other k that we talked about pretty much in every chapter, which is the capital K, which is the equilibrium constant. So the rate constant is a lowercase k, and again, it has to do with the rate, how fast or slow sort of a reaction is taking place. Again, obviously, the capital K, as we talked about for the entire semester here, is about the equilibrium constant and that relationship that we see here. If we just sort of look at units typically here, so the rate is typically molarity over seconds, and the molarity there is usually molarity. So in this particular case, we get a rate constant of 1 over seconds, or reciprocal seconds. And as we'll also learn in sort of this chapter as well, when you see the units associated with the rate constant, it actually does give you some important pieces of information. So for example, when we see a rate constant or a K value here that has units of 1 over seconds, reciprocal seconds, 1 over time, or some unit of time, basically that is very much a first order reaction. And you may remember some first order reactions. We saw that when we talked about nuclear chemistry. All nuclear chemistry or nuclear decay follows first order kinetics. So this sort of rate constant that we see here with a reciprocal second tells us it's first order. And if you also remember, we ended up, I think, using pretty much the kinetic sort of equations. But in sort of nuclear chemistry, that's what they refer to as the decay constant. But it's basically the same thing here. We could also see here we get a nice sort of linear relationship of the rate over the concentration of Br2, which, as I just solved for here, the slope there would equal the rate constant in this particular case. Now, sometimes when we do reactions, as you may be aware of, they may not produce any color, for example, or there may not be any color either produced or starting with color or something like that. And as you hopefully you're aware of, if you don't have any type of color solution or solution with color, there's no way to do any type of absorbance values on it, right? Because everything's going to be colorless, which means you're not going to get any absorbance values. So some reactions, for example, like the one that we see here on the screen, actually is colorless, but will produce, although it doesn't look colorless here, but the gas that's being produced is colorless as opposed to the yellow here, or it's a lot easier to follow the production of O2 in this case. And we can follow the production of O2 by following the pressure, which is where we get our PV equals nRT. And essentially, if you take the ideal gas law, for example, and you solve for N over V equals P over RT. And if you're familiar with the ideal gas law, right, you know that the units that you use in the ideal gas law has to be specific units, and N is moles, and L has to be liters. So that actually is moles per liter, or also known as the molarity of a gas. So one way that you can, if the reaction basically generates a gas, you can basically follow the pressure, because if you were to do this experiment, the temperature most likely would be the same as you're sitting in the same room doing it, which means you basically just follow the change in pressure that's occurring. And you could use something as simple as sort of the ideal gas law to sort of back calculate or relate it to the concentration of that gas and how it's changing. And that's what we see down here. The concentration of the O2, again, is basically P over RT, which is what I wrote up on top. And if you add that time aspect to it, basically you can do this experiment by following over time how the change in pressure is occurring. And basically that will give you the change in the concentration of this gas over time. So this is a good way, for example, to do some type of kinetic study of a gas over a period of time, using the pressure, using the ideal gas law to relate it to concentration versus time. So let's talk, though, what happens when we do have reactions, and everybody's favorite thing, which is, of course, stoichiometry, right? And as you know, whenever you do anything that's sort of related to an actual equation, usually you have to take the stoichiometry into account, sort of the mole-to-mole relationship into account. And it's no different here when we do things like the rate expression. So when we do things like the rate expression, we do need to sort of take that into account. So when we look at this reaction, just like a normal sort of stoichiometry problem, for every 2 moles of A, right, you are getting 1 mole of B, as it says down there. So we do need to sometimes incorporate this into our rate expression. So we could do kind of the similar thing like we did before. The rate would equal minus, because A is a reactant, so again should be decreasing with time. And we take actually 1 over the coefficient here. So that's where we get the 1 over the 2. 1 over the coefficient. The change in the concentration of A over the change in time. When we go to our products, it is positive as it's a product, so it should be increasing with time. And we do the same thing to change in the concentration of B over the change in time. The coefficient here is 1, so that's why we don't see a number there, because 1 over 1 is 1, and we don't typically write the 1 there. So in general, when you are looking at an equation, you could use the rate expression to determine pretty much how everybody in that reaction is changing. So you could figure out, if you just know basically one piece of information, say you know how A is changing over time, you then could figure out how B is changing over time, you can figure out how C is changing over time, you can figure out how D is changing over time. You could also calculate the overall rate of, or the average rate of this reaction by doing that. You could set them all equal to each other, as you can see here. Again, both of our reactants are negative. And again, our products are positive on this side, as they should be increasing. Or you can individually kind of pull them out, kind of like what they did up here, kind of individually, you know, pull them out. And because this is the same reaction, for example, although in this particular case, we don't know exactly what this number is in terms of the rate, we do know that it is exactly the same as this number here. Again, the average rate would be the same for the overall reaction. So this is a very useful sort of equation here that allows you to figure out what is going on in a reaction. And again, you just need a sort of minimal information about somebody in the reaction. You need to know the rate, you need to know maybe how somebody is changing, something like that. And that's pretty much all you need to know. Now, when you do this 1 over the coefficient, that is essentially combining the calculation part where you do the mole-to-mole relationship and sort of how everything's changing. So you're kind of doing it all together. You can, in these type of problems, sort of do them separately. And I guess what I mean by that is you can do a sort of basic stoichiometry problem, just kind of do the mole-to-mole relationship first, like you were doing stoichiometry. And then you could kind of put it into the kinetics part of it and the change in concentration over time. Or if you do it this way, you could kind of do them both together. It sort of takes care of the mole-to-mole relationship for you at the same time. Now, the reason I mentioned earlier that when we do calculate the actual rate, like this number here, it is typically a positive number. And the reason for that is very simple. For example, if we look at A in this reaction, whatever the number may be, we'll go with A to B. If we started, say, with 4 molar A and 0 of B, for example, right? When we're done, it should be decreasing, which means my final concentration is 2 molar. My final concentration over here is 2 molar as well. So when we go to do the change in the concentration part of A, for example, my made up example here, my final concentration was 2 molar minus my initial concentration, which was 4 molar, which gives me minus 2 molar. The minus here and the minus here turns my rate into a positive number. Same thing would happen with B. Now, when we get to something like our product side, when we get to the product side, the final concentration is going to be larger than the initial concentration, which means when we do final minus initial, we will get a positive number. And again, that's why we don't incorporate the negative on the product side, because by that calculation of final minus initial, you'll get a positive number. But on the reactant side, when we do final minus initial, we will actually get a negative number for the concentration, again, because it should be decreasing with time and the final is smaller than the initial. So the take-home message on that is pretty much the rate part here should be a positive number. All right, so why don't you take a second here and write the rate expression for this reaction and see what you come up with, and then we'll talk about it. Okay, so let's take a look here. So again, if we're just going to do this, we can basically set everybody equal to each other. So the average rate for this reaction would equal minus, because CH4 is a reactant, the change in the concentration of CH4 over the change in time. Coefficient here is a 1, so it's basically 1 over 1, which is why nothing's put there. For our O2, also a reactant, so it should be negative as it's decreasing, but it does have a coefficient, so to keep all the stoichiometry correct, minus 1 over 2, change in the concentration of O2 over the change in time. Coming to our products, again, the coefficient there is 1, which means we would have the change in the concentration of CO2 over the change in time. And lastly, we have 1 over 2 for the coefficient, change in the concentration of water over the change in time. I wrote these all equal to each other. Again, you can individually, if you weren't interested in everybody in the reaction, you could just simply go, oh, I'm maybe interested in the CO2. So you could just kind of break it off like this. And maybe you're interested in the CH4, so you could just break off that part of it. And again, if you have numbers or something like that, you could actually place some of these numbers in there and actually come up with some answers. Any questions on how to write that rate expression? And again, the rate expression here is really the thing that relates sort of the entire reaction, the products, reactants, the rate. All right, so why don't we try one actually with a calculation? So I think that's what you have next, I think. Not sure if you have that 02, 03 one or not, but I think you probably figure it out. So why don't you try this one then? Why don't you take a couple minutes here and figure it out. So for this reaction, the change in I minus is from 1 molar to 0.868 in the first 10 seconds. Calculate the average rate for the first 10 seconds and the change in the concentration of H2 over the change in time. So again, I want you to take a few minutes here and actually do it. You should come up with some numbers and see what you end up with here. Okay, so let's take a look and kind of see what we're going on with here. So we have an equation. We have some information given to us, which is I minus. So obviously in the equation here, we are interested in the I minus part. We're looking for H plus, which is right here. So we're interested in this. So sort of a good way to start is just to, if you want, write the rate expressions for each of those, and you can kind of build off of there. So if we look at our I minus, which is the first thing that we have, we see that the rate would equal minus, because it's a reactant, 1/3 will take care of our stoichiometry part of it, the change in the concentration of I minus over the change in time. And for H2, or H plus here, we see that the rate is equal to minus, because it also is a reactant, 1/2, which is our 1 over the coefficient, and take care of the stoichiometry, change in concentration of H plus over the change in time. Now, in terms of information, we really have the information for our I minus, so we could just plug it into here, and that would give us minus 1/3. And up on top there, our final concentration is 0.868 minus our initial, which is 1. And our time, again, is, you could, if you want to do 10 minus 0 seconds would work, or just 10 seconds basically. And this is again important because this is a reactant. We see that this number here, the 0.868 minus the 1, is going to give us a negative number. And because we have that negative number up in front as well, that's going to turn our rate into a positive. And if you do that, you will end up with positive 0.0044. Units here are molarity up on top and S on the bottom, molarity seconds. And this would equal the average rate, as we see here. Any questions on the first part of that calculation? Now, once we have the rate, as we talked about, this rate here and this rate here, it's the same number, which means now we can put that number we just calculated into that second expression. And in the problem here, we're essentially looking to solve for this part of it, which means we need to multiply the 2 to the other side, but not just the 2, it's also the negative should come over there as well. And when you do that, you will get negative 0.0088 molar seconds is equal to how the concentration of H plus is changing with time. This also makes sense if you think about it, because H plus is again a reactant. And as we talked about, we should know that it will have a negative here because it should be decreasing with time as it is changing. Question on that calculation there. So now, as you can see here, excuse me, as you can see here, we did sort of the stoichiometry together with the 1 over the coefficient. So as I mentioned before, if you wanted to, you could have just kind of did the stoichiometry part first, if you like, and then sort of, kind of figured out what was happening by putting that stuff into that expression there. So you could have figured out the rate by, for example, taking the change in the concentration of I minus by subtracting the 0.868 from the 1, and then doing the mole to mole relationship between the 3 to the 2, and then you would end up with that sort of ratio correctly, and you could figure out the rate that way. So the reason we know the rates are the same is when we solve for that rate, as we saw earlier, when you put them right here, for example, or what we see here on the bottom, the rate that we see there is basically the overall sort of average rate for the entire reaction, which means no matter what you do, what part of that reaction that you look at, any of the reactants, any of the products, the way they're changing will equal the average rate. So it will come out the same for everybody there. That's why, as you can see here on the bottom, you can set them all equal to each other, or you can, like we just did in that problem, kind of pull out just the ones you're looking for, because they were all equal basically the same rate. And that's basically the overall sort of average rate for that particular reaction. Other questions on that? And again, you do want to be careful here because sometimes people will kind of multiply, say, by the 2 when they should divide, or divide when they should multiply. So you want to sort of make sure you're careful when you're doing those calculations that you keep those straight. That's a very common sort of error that people make. They don't realize, well, do I need to divide it and then multiply it, or what I should do with the 1 over the number? So you just sort of think about it like a math problem, you know, like we did here on the bottom part. We basically were solving for this, so we need to multiply this to the other side, not divide it, even though you might look at it quickly and go, oh, I need to divide. But in this case, you need to multiply it to the other side. All right, so why don't you try another one here. If 2.4 times 10 to the 2 grams NOBR decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes, what is the average rate of BR2 production in molarity over seconds? So take a couple minutes here and see what you come up with. Okay, so let's take a look at this one here and see. So in this case, we're given grams of NOBR. It's decomposing in a basically 200 milliliter flask in 5 minutes. We want to find the average rate of our BR2 production in molarity per second. So again, if you just want to kind of approach it like we did the last one, we could really take the two things that we have information about or we're trying to find. So the first thing is the NOBR. And if we write the rate expression, that's going to be minus, because it's a reactant, 1/2 change in the concentration of NOBR divided by the change in time. We're interested in BR2 as well, and that would be the rate equals, it's a product, so it's positive, also has a 1 for the coefficient, so it's 1, and basically would be the change in the concentration of BR2 over change in time. So we do have grams and we have the molar mass given to us, so we can figure out the moles of NOBR by taking 2.4 times 10 to the 2 grams and dividing it by the molar mass, which obviously if it was not given to you, you would find on the periodic table. And if you do that, you will get 0.02202 moles of NOBR. I'm also going to change my minutes into seconds because ultimately we're looking for seconds. Again, at some point you need to do that. So we'll just do our 5 minutes, and I think that's a minute is 60 seconds. So it's going to give me 300 seconds. So we basically now have the moles, we have the seconds, and we also have 200 milliliters, which is 0.2 liters, right? So if I take the moles of the NOBR divided by the liters, that will give me 0.1101, we'll call it. Molar here of NOBR. So we now have sort of the top part that we need. We also have the bottom part there, just to make sure I hit everything right there and miss a 0 anywhere. 2 to 2 divided by 109.91 gives me definitely not that. That's a really badly punched in number there. Should we use the right number there? There we go. Let me try that again here. I think I lost a number along the way there. All right, one more time here. 2.4 to the 2 divided by 109.91 should give me a better number of 2.184 moles. That seems better. Divided by my 0.2 gives me 10.92, which is much better as well. So let me get rid of that. Sorry about that. That didn't look too right to me. Let's see. There we go. So we should end up with 10.92 molar NOBR if you actually punch it in correctly in your calculator, which I probably would highly recommend, I suppose, right? I guess so. All right. So now that we have the right molarity here, we probably want to put that in there before I make any more bad mistakes there. It's okay. I was more of a history major. It's okay. So we're going to put this in here. This is going to be 10.92 molar divided by my 300 seconds. And I am going to make this negative. And you may be wondering why I'm making it negative. So the number that we got here is really the result of the change in the NOBR, which is our final minus our initial. And since the NOBR is a reactant, what we know about it is it should be decreasing with time, which means technically speaking, when we did final minus initial to get that 10.92 number, technically speaking, it should be a negative 10.92 because the final concentration should be less than the initial. And more importantly, like we talked about, the rate number here does need to be positive. So if I did not make this negative, I would end up with a negative rate, which you should not have. So if we do that correctly here, and now I think I got all the right numbers going on, we will end up with 0.018 units here, molarity per second, as the rate. Now remember that we're interested in the BR2 over the change in time, and we can see that the rate equals the change in the concentration of BR2 over the change in time, which gives us 0.018 molar seconds is how that guy is changing. Also works out very nicely because that is a product and that number should be positive, which it ended up being as well that we did it here. Any questions on that calculation there? Again, as long as you use the right numbers, things should go okay, hopefully for you. And again, a reminder that, like I said before, if you wanted to kind of from this part, you could have just done the mole-to-mole relationship between the NOBR and the BR2 and then plugged it into, here, and you would get the same answer. So again, like I said, on these problems, you can do sort of the stoichiometry part separate if you want, or if you do the 1 over the coefficient, it kind of combos it for you and kind of takes care of the stoichiometry part for you. So the question is, did we not do the final minus initial? Technically speaking, it was, but the end result was that they kind of gave you the answer to the final minus the initial. The only thing that they didn't really tell you was that it was final minus initial. So you have to know that because it's a reactant, you have to put that negative in here. This is sort of, this number that we got here is sort of the result of like final minus initial in a sense. And so instead of telling you, hey, you started with, 500 grams of this and ended with, 260 grams of this, and so you subtracted it, it basically just kind of gave you the overall ending of final minus initial in that particular case. Let's see. It is the same rate. It's the same rate because remember that the 1 over 2 really is the stoichiometry, right? And it's really the mole-to-mole relationship is really what the 1 over 2 represents. So although it seems like you're taking half of it or something like that, remember that it's sort of like the mole-to-mole relationship in a stoichiometry problem. So in order for this reaction to proceed correctly, right, this reaction needs 2 moles of NOBR to produce 2 moles of NO and 1 mole of BR2. So for every 2 moles of NOBR, you get 1 mole of BR2. So that mole-to-mole relationship is what allows this reaction basically to take place sort of correctly, if you want to think about it that way. And when it would take place correctly with that mole-to-mole relationship, it would have an average rate overall of how much it's producing. And so that's why when we look at it, even though it looks like you're taking half of something, and how could you take half of something and it still equals the same rate? The idea there is that mole-to-mole relationship that's basically producing that rate. And in this case, it's a 2-to-1 relationship, which in relationship to NOBR and BR2 is essentially half the moles, right? 1 over 2. So that's essentially what that relationship is there. So remember, when we look at the rate here, that's the rate of the overall reaction. And remember, for this reaction really to take place correctly, you need everybody to come together in the right proportion to produce the product, right? And for that reaction basically to proceed sort of correctly, right? In that mole-to-mole relationship. And that's what the 1 over 2 is. And the other guy is basically just, so it's a 2-to-1 relationship. Other questions on that? And again, if you sort of did the opposite approach where you kind of did the stoichiometry first, what you could have done just to kind of maybe tie the 1/2 relationship a little bit more here is, if you did this problem sort of in a more stoichiometry sort of approach, like a normal kind of stoichiometry approach, if we picked it up right here with the moles, which was converting it to 2.184 moles of NOBr. Again, you could have done just a basic stoichiometry problem where you said for every 2 moles of NOBr, you get 1 mole of Br2. And by the way, if you could kind of notice it there, that is your 1/2 relationship, right? So again, that's sort of where that came from, is basically the dividing and multiplying part of the mole to mole relationship is what that 1/2 is. And you get your moles of Br2, which would be in this case 1.09. And then at that point, you could have divided it by the 0.2 liters, which got you 5.45 molarity of the Br2. And again, at this point, you then could have used the seconds and divided that by the 300 seconds, and then you would end up with the same answer as here. So again, although it looks like you're taking sort of a fraction, it really is sort of doing the dividing by the moles, multiplying by the mole to mole relationship for you in sort of one step, rather than doing it separately like we did here. And again, you can kind of see that's where the half comes from right there. It really is nothing more than that mole to mole relationship from the balance equation, basically the stoichiometry of it. Other questions? Okay. So obviously, if you're given some information, the rate expression is really a good one to sort of think about. It allows you, with very sort of minimal information about just one person in the reaction, either reactants or products, that you could pretty much figure out how everybody in the reaction is changing. You could also figure out what the overall rate of this reaction would be as well. So let's talk about some factors that do affect sort of the rates of reactions. And some of these we will talk about as we sort of go through this chapter. But for example, the nature of the reactants. So what sort of physical state they're in has a big effect on sort of how fast or slow a reaction may proceed. So typically smaller molecules will react faster than larger ones. Again, smaller molecules are smaller. They can move around a lot faster. Gases obviously would react a lot faster than liquids, and liquids would react a lot faster than solids. Gases, just by the process of them flying around, are going to come in constant contact with other gases and so forth, other things, and the reaction would probably kick off a lot faster. Liquids as well, right? In liquids, you pretty much have ions floating around, right? And those ions are floating around and they can come in contact with other ions relatively quickly, as opposed to if you just drop like 2 solids on each other, not much is going to happen there, right? Because nobody's moving around. They're just kind of sit there. Not very much would probably take place very fast. If you do have solids, sometimes powder solids are more reactive than blocks. Again, greater surface area for the reaction to take place. So it will usually kick off a lot faster. Certain chemicals are more reactive than others. So for example, metals, which you may be familiar with when you talked about perhaps single replacement reactions, the activity series of metals, typically a big list of metals, and in the middle is hydrogen. And anything kind of higher on the list will replace anything lower on the list because they're more reactive. Anything lower on the list is less reactive than anything higher on the list. So in like a single replacement reaction, those reactions would not take place. As I mentioned before, ions usually will react faster than molecules. Again, ions are kind of free, if you want to think about that, already floating around the solution, ready to sort of react, up front. They don't have to break any bonds like we do in sort of molecules. Temperature is a big effect on sort of reaction. Temperature can a lot of times increase the reaction rate. And if you do sort of the opposite, it can decrease a reaction rate by slowing it down. So if you kind of heat up a reaction, you know, it'll go quicker usually. If you throw everything on ice, it typically will take longer for that reaction to take place. So just in general, if we increase, for example, a reaction by about 10 degrees Celsius, for a lot of reactions, that usually will have an effect of almost doubling how fast that reaction would take place. And there is sort of a mathematical relationship that we'll see a little bit later on in this chapter, which deals with temperature, rate constants, and the Arrhenius equation. And we'll see it a little bit later there, where you could kind of figure out things like activation energy, temperatures, and obviously rate constants, how fast or slow a reaction will take place. Now, a catalyst is another thing that will typically affect the rate of a reaction. And a reminder that a catalyst, again, is a substance that is not a reactant, nor is it a product. It doesn't get used up in a chemical reaction. It is there usually to facilitate that reaction to take place faster. And that's usually what we are talking about when we talk about a catalyst, is the idea that it will speed up a chemical reaction. There are catalysts that will actually slow down chemical reactions. And those are sometimes referred to as negative catalysts, but probably 99 times out of 100, if somebody is talking about a catalyst, they're usually talking about it in the sense of sort of speeding up a chemical reaction. And we'll talk about how it does that a little bit later on in this chapter as well. But catalysts can be homogeneous or heterogeneous, which means the catalyst can be in sort of the same phase as all the reactants, maybe different phases. You can almost think of a catalyst as sort of a place where everybody could come together a little bit more efficiently for a reaction to sort of occur, rather than maybe floating around trying to find each other. They all go, oh, we're all kind of attracted to this center location. And when they all get there, they then can start to react a little bit faster than they would if a catalyst wasn't involved. Now, there you go. So generally, the larger the concentration will have an effect on how fast a reaction will take place. So if you have a larger concentration of reactants, that means, technically speaking, in order to get a large concentration or molarity, since molarity is moles per liter, in order to get this to be a big number, you should have a pretty big number of moles, and molarity is moles of solute. And hopefully you know that the moles of the solute is essentially in the reaction what's reacting, right? So if you have a higher molarity, you have more moles of solute. More moles of solute means you have more reactants probably involved, and more reactants mean they don't have to go hunt each other down. They're most likely going to come in contact with each other a lot faster, and thus the reaction would proceed a lot faster. Obviously, the opposite of that is true. If you sort of have a lower concentration, the reaction may take place slower, or maybe not even at all if you don't have the right concentration. But again, they have to go kind of find each other. Concentration of gases depend on the partial pressures of the gases. The higher the pressure, the higher the concentration. So as you hopefully remember also from gas laws, when we have high pressures, we typically have small volumes. And because we have small volumes, all the gas molecules are pretty much near each other, which means they don't definitely have to go hunt around to find each other. They're most likely going to come in contact with each other very quickly, and the reaction would probably proceed very quickly as well. And again, some of these guys we will talk a little bit more about as we go through this chapter. Any questions on that there? All right, so let's then talk about the rate law. And the rate law is basically an expression that basically relates what is happening in a particular chemical reaction. And a couple important things, good talk, a couple important things that we see about the rate law is, this is again an example of a rate law. And this is the rate is equal to K, which again is our rate constant. concentration of A and B to the X and Y. So the X and Y are what are referred to as orders. So again, there's sort of, if you want to think about it, like sort of the proportion of those guys is necessary for this reaction to sort of take place in the correct rate to occur at the sort of correct speed. Now, if you want the overall order of the reaction, you basically could add those together. So if you add up all the individual orders, it gives you the overall order of a particular reaction. Also very important, if you look at a rate law versus what we were talking about a little bit earlier in this chapter, which was the rate expression. In the rate expression, we deal with both reactants, products, everybody involved. When you look at a rate law, the only thing that's involved is, as you can see here, just the reactants. So it's only the reactants in a rate law. Products are not included in the rate laws, so we're not really worried about the products here. We're just simply worried about the reactants. Now, a couple of important things as well is X and Y. These guys are found experimentally. They are not the coefficients in the balanced equation. So at this point in this class, we've done a lot of things where we go through the equation, we take the coefficients and they become like the exponents, like what we do in equilibrium expressions and so forth. But this is the one place where the orders, the X and the Y or the Z or however many orders you got going on there, are not taken directly from the coefficient. They do have to be found experimentally, which means that typically speaking, you will be given a table, and rate laws typically are found experimentally. So you'll be given a table, and we'll see a table in a couple of examples coming up. But basically in this table, you will have the concentration, say, of A, you'll have the concentration of B, and you'll have the rate in like molarity per second. And you'll have like trial 1, trial 2, trial 3, trial 4, whatever many trials they might have done for that. So in a problem like this, you typically will be given a table of information, experimental information. And there's one or two ways you could kind of approach it. You could approach it by just looking at the information in the table and trying to figure out how the rate changes versus how the concentration changes. Most of the time, people probably have a very hard time doing it that way. So usually a more easier way of doing it, or a more sort of mathematical way of doing it, is just that, to do a mathematical sort of approach. And usually the mathematical approach is we'd go rate 2 divided by rate 1 equals K times A to the X, B to the Y, divided by K to the A and B to the Y. And when we say rate 2 and rate 1, we don't mean that you go to the table and grab entry number 1 and entry number 2 and put it in there. What you want to do when you go to this table is essentially find 2 entries, and you want 2 entries where one of the concentrations remain the same and the other one varies. So for example, if I just made up some numbers, let's say this guy was 4, this guy was 4, this guy was 2, and this guy was 4, and the rate here was 1.2, and we'll go with 2.4, for example. So for example here, if I looked at this table and this made up numbers here, I would see that the concentration of A for experiments 1 and 2 remains constant, while the concentration of B varies. And usually in math, you want really just kind of like one unknown. And if we do that, where we keep the concentration constant in one and varying in the other, we could use this formula up here to help us solve for, the order. And we could do that by taking the information for each entry. And typically speaking, if you want kind of a nice whole number approach, usually you take the guy that has a larger rate and put it on top. So what that means is what I'm going to do is take experiments 1 and 2 here. And everything for number 2 is going to end up on top. So my rate is 2.4 equals the constant K times the concentration of A, which is 4 to the X, times the concentration of B, which is 4 to the Y. And everything that I just wrote there all came from entry number 2 in my made-up table. Now, I would do the same thing for entry number 1, take all the information from entry number 1, and I would put on the bottom. So my rate was 1.2 K. Concentration of A was 4 to the X and 2 to the Y. So now we could do some math with this to figure out what is going on here. And if we do that, if I take 2.4 divided by 1.2, I get 2. Now, when we come to this side, the K on top and the K on the bottom, that is known as the rate constant. And since it's called the rate constant, that number should be the same since this is the same reaction that's taking place. So although I don't know what it is at this moment, I do know it's going to be the same and they're going to cancel out. Now also because this is the same reaction, when I come to the 4 to the X and the 4 to the X, although I don't know what X is at this moment, I do know because this is the same reaction, it should be the same number, which means that technically speaking, this should cancel out. That then leaves me 4 to the Y divided by 2 to the Y, which would give me 2 to the Y. So essentially what I am left with at this point is 2 equals 2 to the Y. You probably could figure out what Y is equal to. Y would equal 1 in this case. By the way, if it's a little bit more complicated, you could take the natural log of both sides and divide. And you'll get the same idea. So in this case, you take the natural log of 2 divided by the natural log of 2. I just made up those numbers, the 1.2 and the 2.4. Those are the rates in my made up table over here. Again, I just made up all the numbers in that table. And that would give us the order with respect to Y. You would then go back to that table. I won't make up more numbers, but if you go back to that table, what you would then want to do is go, okay, I held A constant the first time. Now I want to hold B constant. So, you know, maybe there's another entry where it's like, you know, 2 and a 2 or something like that. And then here we do 1 and 3. B is constant, but A varies. So the idea when you go to that table, and we'll see one with actual numbers tomorrow, I guess, as we're at the end here. You want to go where you have basically everybody constant except for one concentration. And again, that allows you to have basically one unknown, and you can sort of mathematically solve for what it is. Any questions on that up until this point here? Okay, so we'll stop here and then we'll pick up fresh here next time, doing some examples with real numbers and values and stuff like that. Any questions on anything we talked about today? All right, so up on tap is an experiment. 23, I think. We're almost to the end there. It's got to be near. So it should be, I believe, complex ion, some type of plot, and figuring out basically the formula of a complex ion. I just don't recall what the title is of it. All right, make sure you put here, and then we'll see everybody in about 10 minutes or so with that one. And again, I think it's experiment 23.